In this video, we will derive Gibbs' equation using the Clausius definition of entropy change. So the Clausius definition, created by Rudolf Clausius, is based on his theorem which says for a reversible cycle, the cyclic integral of heat transfer divided by the temperature at which heat transfer occurs must be zero. Okay, so if we were to write this mathematically, we would say the cyclic integral, so the integral from one point going to another point and then coming back to the original, of the change in the heat transfer divided by temperature is equal to zero. So let's see how we can apply this to change in entropy. So let's start with our diagram here. Now for this diagram, we've got a couple of paths here, A, B, and C. We're just going to focus on A and B, the reversible paths. Okay. So we're going to analyze a process going, or a cycle that goes from 1, goes along path A to point 2, then goes along path B back to point 1. If we break the cyclic integral above up, we can get the integral from 1 to 2 of the change in heat transfer over temperature along path A plus the path from 2 to 1, so going back from 2 to 1 of the heat transfer over temperature of path B. And that will equal 0 according to the theorem. So let's move one of these terms to the right side, and we get negative term. To get rid of this negative term, what we're just going to do is flip the integral. So if from 2 to 1, if we switch it from 1 to 2, then all we've done is we can multiply by that by negative 1, and so that negative goes away. Well, now what you see is from 1 to 2, whether we go along path A or path B, it's the same. Well, if it's path independent, remember that's one of our definitions of a property. So we're going to refer to this quantity inside the integral as a property, and we're going to call that property entropy. So since it's discrete change in our heat transfer, we're going to call this our change in entropy is equal to the change in heat transfer over temperature of a reversible path. All right. If we were to then integrate this quantity, we would get the change in entropy 2 to change in entropy 1 is equal to the integral from 1 to 2 of change in heat transfer over temperature reversible path. Now notice these are capital S's here, so this is the entropy, not the specific entropy, but this is an extensive property of entropy. There is also an intensive property. We're going to stick with the extensive right here. So using this is an equation that we'll use to define entropy, the change in entropy. We're going to utilize now this definition for our change in entropy as we derive the Gibbs equations. So Gibbs equation 1, we're going to look at a reversible process in a closed system, and we're going to assume that the kinetic energy and the potential energy equal to 0. So to get the Gibbs equation, what we do is we take the conservation of energy in its differential form. So the conservation of energy is our energy transfer is going to equal to our change in our energy of our system. And since kinetic and potential energy are 0, we're just looking at internal energy. And now we're going to make some substitutions. So substituting for that change in heat transfer, we're going to rearrange how we just defined that discrete entropy to say that our heat transfer equal to temperature times change in entropy. And going back to moving boundary work, our definition, we're going to say that our change in work is going to be our pressure times our change in volume. Or excuse me, our discrete work is our pressure times the differential volume. Well, then we just substitute this into our conservation of energy equation, and what you get is temperature times differential entropy minus pressure times differential volume is equal to differential internal energy. This right here is the extensive form. If we rearrange these with just temperature and entropy on one side, is our extensive form of the Gibbs equation 1. We can do an intensive form by just dividing by mass. So both of these equations are forms of Gibbs equation 1. Either one, one's extensive, one intensive, but they're both Gibbs equation 1. Now to get Gibbs equation 2, all we're going to do is we're going to apply enthalpy to Gibbs equation 1. So remember that enthalpy is equal to internal energy plus pressure times volume. If we take the differential form of enthalpy, it's equal to the differential internal energy, and then if we take the derivative of this quantity, pressure times volume, according to the chain rule, you get pressure times differential volume plus volume times differential pressure. We then substitute that into Gibbs equation. We arrange this in terms of internal energy, differential internal energy, and substitute it into Gibbs equation 1. Now you can see we've got a negative pressure times differential volume and a positive. Those will cancel out. And Gibbs equation 1 will simplify down to temperature times the change in entropy is equal to differential enthalpy minus volume times the change in pressure. Or in intensive form, it's just divided by mass, and we get the specific properties. Both of these equations are Gibbs equation 2. So why do we have the Gibbs equations? Well, the Gibbs equations are statements of our conservation of energy in terms only of thermodynamic properties. So conservation of energy is comparing energy transferring into the system through work and heat transfer with the change in the energy states. What this allows us to do is define conservation of energy only in properties.